Okay. Okay, I'm going to talk about Kirchhoff migration because I was asked to do so. So first, I'm gonna give some background and definitions such that this video can stand on its own. But if you're just watching it to know what Kirchhoff, how to do it, you can just probably skip to number 4 ahead in the video. I'll give an example of the processing that I do in the processing pipeline. Some academics about the scattering process. Then I'll get to the meat where I go into Kirchhoff migration. First, I give an intuition on how it works. Then I'll give you an algorithm. Oh, I should mention this is all 2D only. And then to actually use it, we need a way to calculate angles. So I call it the transmission angle algorithm. And I'll code in MATLAB real-time a migration algorithm. So you can follow along and code with that. So I'm going to start with some background information. So this is, let's say, how our data collection works. This is using the radar that we have right now. So we give a coordinate axis, z, x, and y coming out of the page, and draw right here the ground with some buried target. Now we have some antenna here at height z is equal to -h. The target is at z is equal to d. Of course, this is z is equal to 0. Now, what we do is in 2 dimensions, we scan the antenna along x here. So our x equals 0 can be any point. It's really arbitrary. But we scan the antenna along, and the antenna shoots out pulses, which get reflected from the target, and we record what that signal is back at the antenna. We call this an A scan. So an A scan is a time domain. Well, that's not really general enough, but it's a single signal taken at one position x. Now we have a time domain signal, and our signal looks something like this. So if I call it s of t for some signal, and then we have the time axis, our A scans generally look something like this, where we have something like this going on. Now what's happening here is this is usually the coupling signal from our transmit to our receive antenna. The ground signal is generally, so the ground return is generally overlapped by the coupling signal. So it'll look weird, but the ground return is generally at some point here. So inside coupling signal. And then usually our target is like some magnitude here. This is pretty far off, so this would be a relatively deep target signal. And then maybe this is clutter or maybe something else. So generally with an A scan, we don't get much information because there's so much junk in it. So we take multiple A scans and call it a B scan. So this would be, a B scan is a collection of A scans at multiple X positions. What this really does is it resolves what we could academically say is it resolves ambiguity in the X direction by taking multiple X scans. So the B scan is what we generally see when we're looking at data, at least 2D data. It's the most accessible generally form of data that we see. Sorry, I'm trying to bring up an example of a B scan. Okay. So this is an example B scan. Bring it up here and increase its size. So you see each column is one A scan. So going along here, we just take a single slice, that's one A scan. Each row is a single time bin. So along here, there's a constant time. So by scanning, we can start to see things pop out in the B scan. So you see this is obviously the coupling region up here, where the two antennas are talking to each other. This right here is the ground bounce. This is measured data, by the way. And we have two targets here. Target 1, target 2. And this was taken in the sandbox that we built. So these are walls of the box. And then over here is the Kemper floor. So you can just see that by looking at the B scan. But what's more interesting is there's a lot of stuff in there. And if we present data like this, people are going to say, what the heck is going on? So we need to process it. And that processing is what I'm going to talk about next. And I'll give an example processing pipeline. So in lieu of actual real pictures, I'll just draw cartoons to get the point across. So in the pipeline, first we have data collection. So this is, for example, in the actual setup, we have an actual target here. And, this is some soil that we know the permittivity of. And there's some antenna that we know where we take the discrete X scans of. So we know some vector X. So after that data collection, we get the raw data. This is the B scan. This is right here. This is an example of the raw data. So to kind of cartoon it, we have a bunch of coupling, ground return, maybe a target hyperbola there. Make that a bit more fancy. So first, we do, well, it depends on the data, but I'll say first we do jitter compensation. So if we have in a real-time receiver, we do time of arrival jitter compensation, and this is lining up A scans in time. If we have a equivalent time receiver, I'd say nothing yet. You're good for now. So you're still going to have relatively, you're still going to have these lines in here. So number 4, now we get to the changes. So I'll say now we do background removal. This is BKGR. That's an anagram I use a lot. So the way that we do background removal is we subtract the mean. So the MATLAB code for this, I'll give the MATLAB code and the real equation. So if we have some B scan B, we'll say B is equal to B minus the mean of B across the second dimension. So of course the first dimension is down here, and the second dimension is the columns. Now the real equation for this would be say B is equal to, well, we can index it, B of X and T. For sake of consistency, I'll do B of T and X is equal to B of T and X minus 1 over N sub X. K is equal to 1. K is equal to N sub X. Or you can do like a sliding window type of thing. B, T, X sub K. So this is just the average, that's just the exact same thing, but in this equation you actually implement it. This is just the way to understand it. The way and the result of this is you get rid of all horizontal stripes, generally. So now you only have the target hyperbola. Background removal does remove a bit of the target. So if the rest of it, the rest of the scan was 0, and you only have that target hyperbola, then you get a version of a scaled version subtracted from all the other pixels. But generally, we just accept this loss. So next, and the last one I usually do is I usually band limit. Generally, you could interchange 4 and 5. I can see why you'd want to do 5 before 4. But I've personally found that band limiting after background removal is nice. So let me give you 2 examples. So the first system we had was I used 0.3 to 3 gigahertz band. So if you're designing a filter, call this H of F for the magnitude, frequency here, and also considering the negative frequencies. I use a filter that looks like this. This is -3, -0.3, and 3. So just a rectangular window. You can get fancier with it. The reason you would want to get more fancy with it is if you wanted less group delay variation, but I chose frequencies out of the range that we really care about for this. And for our new system, we go, I'm personally doing 0.3 to either 5, 11, or 21 gigahertz, depending on how far we go. I guess we haven't decided what exactly we're doing yet. And it'll be the same idea as here. Nothing in my cartoon would really show the difference, so it would still be roughly like this. And the way that you filter, I forgot to mention. So in MATLAB, I'll say B sub f for the frequency version of it. You take FFT shift FFT B brackets 1 for the first dimension and 1 for the first dimension. So this FFT is taken on this domain. Now I've shown that also filtering over here, generally high pass filter or low pass filter in the X domain is good too. So how to do that, you would just replace this with 2. For X, use 2. And then since you'll have a frequency vector, you can just say B of F, abs, for example, a low pass filter, abs of F less than F min is equal to 0. That's a very simple way to do it. So now that we have basically pre-processed data, we can take it into imaging. So this will be the step where I stop doing stuff. So number 6, imaging. And in this case, we take these hyperbola and just transform it into a single point. And that's what the purpose of this example is for, to teach you how to take this hyperbola and turn it into this point. In reality, let me get an actual image. In reality, we don't get a single point because because our waveforms are not single peaks. So here's an example of the image of that migrated, or the migrated image of that example B-scan I had earlier. So there were 2 targets, and we really get 3 peaks here. We go 1, 2, 3. That's because essentially the waveform of our system looks something like this, where we have 1, 2, 3 peaks. And that's what we get reflected off the target. There are ways to, that I've read, to fix for this and only have 1 peak. But that's a different type of imaging. So just Kirchhoff migration, generally you get these multiple peaks. And that happens with all types of migration. So this is where we stop. I mean, realistically, then you go on and do detection. So you have some probability of detection and some probability false alarm. And you say, hey, we achieve 90% probability of detection at 0.1% probability of false alarm. That's great. Okay. So I'm going to give a few words about scattering in general, that's really useful to help understand Kirchhoff migration. So I'm going to draw a little box to help us understand. So we have some target here in some soil, some epsilon soil, and that target you can describe as epsilon plus delta epsilon as a function of x and z. Of course, again, our coordinate system is like this. And we have our antenna here at negative h. And this antenna will radiate a pulse E at the electric field at the x position xa, z position negative h, and in general we'll put a t here for time. So there's two types of problems that we want to know here. There's the forward problem and the inverse problem. And Kirchhoff migration is the inverse problem. Now, why does that matter? So to tell you why that matters, I'll first describe what I mean by forward and inverse. So the forward problem is you're given this delta epsilon xz. You want to find E. You want to find the scattered field. So I guess we could also put incident and scattered. Find the E scattered. And you're also given, but that's kind of assumed. So you're finding the scattered field in the forward problem. Now this, of course, is governed by Maxwell's and is easily, I put in quotes, solvable. So what I mean by that is the forward problem is well posed. So it has one solution, unique, has a continuous dependence on this delta epsilon value, which, so if you change that delta epsilon by a tiny bit, you'll get a tiny change in the scattered fields, and you'll know what that is. It's also nonlinear, which is kind of obvious given that it's governed by Maxwell's equations. So the inverse problem, which is what all imaging algorithms are, is given the scattered field, find this delta epsilon function. So fortunately, this is also governed by Maxwell's, but not easily solvable. So in general, the inverse of a nonlinear process is very difficult. And the reason why this one's difficult is this is ill-posed as opposed to being well-posed for the forward problem. So ill-posed means, one, impossible to retrieve all, maybe I spelled that wrong, data about this delta epsilon. So number one, it's impossible. Don't even try. So two targets could create the same scattered fields. Similarly, invisible targets exist. You know, there could be a combination of two targets that, you know, maybe cancel each other out, or one target is just really funkily designed that it's invisible and generates a scattered field that is consistent with having no target there. So this is why all the imaging is difficult, and usually they look bad. So now that I've said that, let's talk about imaging. So this is what Kirchhoff migration is. So what this effectively does is you have some GPR B scan with time and X here. We got some sweet target hyperbola. It's been pre-processed, and Kirchhoff migration is the arrow that brings it to what we call an image, which is just a single point, ideally, which now has depth and X. I use the subscript Q here for query, because you don't have to calculate all X values, so you just calculate the sub Q for query. So let's think about this. How would Kirchhoff migration work? So number one, where there is a hyperbola, there must be a target. So if a point, that's some point here, contains a target, there, or the point will be on a hyperbola. These two statements aren't necessarily equivalent, but the logic basically means if you see a hyperbola, the target should be at the peak of that hyperbola. So let me draw another picture to get the point across. Now I'm doing it in reverse, where this is the image, and we have our query points here, and then this is our B scan. We have our target here. So let's choose this point right here, this pixel. This is our, we'll call it XQ, ZQ, just so I don't say too many things. So to translate the logic above, if XQ, ZQ contained a target, a hyperbola would spawn out from it. That's kind of the wording that I use. It spawns out the hyperbola. If it contained the target, if this point, which let's say corresponds to right here, contained a target, the hyperbola would look something like this. And of course, going off the screen. So that's what that sentence says. So now we want to see how likely it is that XQZQ contained a target. So how likely is it? Well, we'll do our comparison using energy. So what we want to do is how much energy does that hyperbolic curve contain? So sum every point along the hyperbola. If it sums to a high value, so let's say if we get a high value, there's probably a target there. Low value, probably not. Okay. So of course it's not that simple, but it is following that general rule. So the actual equation for Kirchhoff migration, let's say we have some image I at the query point. This is equal to the integration, so we sum from minus infinity to plus infinity over the antenna positions. So each scan point, I forgot to say, each scan point in here, x sub a, is what we're integrating over. And what we integrate in here, I call the kernel. This is cosine theta over square root magnitude r, half derivative of the electric fields at xa, and t is equal to t expected. So what I mean by, so let me define the things in here. So let's say I is the image, just the image, maybe image power would be more fitting. Theta is the view angle of the target. So you could either take it to be theta in air or theta in ground. No one ever really specifies. I think I take it to be theta in ground. This r is the distance from the antenna to target. Well, supposed target. So that would be to point on the hyperbolic curve. What does this half derivative mean? This is kind of a thing dropping out of the math. It's a property of a Hankel function. So the half derivative, the way you really implement it is you just take the Fourier transform and then multiply by j omega to the half. So if you say that e of x omega is equal to the Fourier transform of e x t, let's say e r for fun, then d1 half dt half e xt is equal to j omega to the half, well, the inverse Fourier transform of j omega to the half e carets x omega. So what you're going to do is you're going to take the Fourier transform of the electric field with respect to fast time, and then just multiply it by j omega to the half, and then inverse it back. So this x, moving on, we have xa is antenna scan position, whereas this xa is a member of some vector x scan. And then this t expected is the expected time that a hyperbola would occur. Now that doesn't really make sense yet, but if I draw this V-scan again, it'll be quite clear. So if we have some target here, where this is time starting from 0, this is x. So if there was a target here, which it looks like there is, you would expect for this x position, you would expect a hyperbola to occur at this time. That's what t expected is. And I'll go into more detail when we do the transmission angles idea. But basically, I'll give the formula right now. 2h, which is the height of the antenna over speed of light, times the secant of the angle in air, plus 2 some query depth of secant theta in ground, or c of the square root of epsilon. So this is the formula, and it tells you, it's just, say you had a target at some depth. In this case, in t expected to be, say, the ZQ, and you view it with a set of angles, theta A and theta G. We, of course, have some epsilon. How long does this take? And then that's, that result is that equation right there. And of course, theta A and theta G depend on x here. So now you see how, despite looking fairly simple, as in there's not much dependence on x of a here, there's actually quite a bit in this t experience, or t expected. Of course, the xa, this r depends on depth, of course, because this r is the length, path length from here to here. And of course, the theta depends on x of a as well. So I'm going to go over how to calculate the Kirchhoff migration. So I'll say algorithm. So this will be some sort of pseudocode here. So say select a query point xq and zq. So that is in your image the pixel that you want to populate. That's your xq, zq. Now, in your B-scan, you're going to determine the expected target hyperbola for each XA. So for a single, of course, this is the XA axis. Your target hyperbola is going to look like this, but you want to do that for each antenna position here. Oh wait, I'm mistaken. What I mean is for each XA, you want to know what this T expected is. So basically you're drawing out this hyperbolic curve. So the way you do that is, number one, you solve for transmission angles. So theta A is angle in air, and theta G is angle in soil. Now to draw that out, we have our antenna here and our target here, theta A, theta G, and some permittivity. Now this is just governed by Snell's law, but I'll give you a simple way to do it. So these are functions of x sub A, and then of course you calculate your T expected as such with 2h secant theta A or C, which is the time in air plus your 2d secant theta G over C root epsilon, which is time in soil. So now you have this T expected, and you take the electric field value at each time over this XA, and you calculate the kernel. So now you calculate the kernel of the Kirchhoff migration integral. And this kernel is, of course, K is equal to cosine theta, let's say G, over square root R, d to the half dt half, E at some XA, T is equal to T exp. So now it's pretty simple. Now you just integrate. And of course you do this for each XA with respect to XA, which is what the Kirchhoff migration is. So now you have I is equal to integral negative infinity to infinity, or whatever your limits are, of K dxa. And then you store the results in the corresponding pixel. The pixel is xq, zq. And then you just repeat. So bring it all the way back up here and calculate it all over again for a new pixel. So maybe it's a little confusing. It's once you write it, you'll understand it for good. But before I get to the MATLAB script, the example script, let me first give you a method. So method to determine theta A and theta G, the angles of transmission. So there is a more complex method. I'll call this the 2D method. There's a 3D method which I use now in my scripts, but it is too complicated to do really quickly, to script really quickly. So I'm going to draw a more verbose diagram of a GPR setup. So this is target, well, soil, antenna, and this antenna is at height h, and this target is at a depth d, or z sub q. So the path will follow the light of the light will follow the path of least time given by Snell's law. So it'll look something like this. And we have your theta G here and your theta A here. So here is how we solve this problem. What we do is we write two equations. We write one for the position of this, I call it the soil, the intermediate point where this ray would strike the soil. We write it looking from the target and looking from the antenna. So that's two equations. So looking from the target, call it xi. Looking from the target, we have xi is equal to what we have. This is called xt. This would also be xq. Xi is equal to xt minus d tan theta g. That's our first equation. Our second equation is xi is equal to xa plus h tan theta a. And also theta g is equal to inverse sine of 1 over square root sine theta a. And for completeness sake, we'll say sine -1 root epsilon sine theta g. This is just Snell's law. So what we want to do is we want to combine these two equations actually, because there's only one unknown. So we set them equal to each other. We say that equation 1 is equal to equation 2. So xt minus d tan theta g is equal to xa plus h tan theta a. And then what we will do is we will take xt minus xa minus d tan theta g minus h tan theta a is equal to 0. Now we can solve for a theta because we have these two equations here. I have found that it is more computationally robust to substitute in for theta a. So we can do xt minus xa minus d tan theta g minus h tan arc sine root epsilon sine theta g is equal to 0. Now, if you notice, this is only valid. This equation here is only valid if x sub a is less than x sub t. Only valid for x of a less than x of t. So the way we can actually solve that is we notice that right now x of t minus x of a would be greater than 0. But if x of a was greater than x of t, we would have it less than 0. So actually we can make this universal by doing absolute value instead of just the regular expression. Now we can call this is our golden expression. We can call this a cost function, which I think is quite fair. So this f of theta sub g is our cost function. And we have our expression of the true theta sub g. I'm screwing up the, well, actually, I can just do this. Our theta sub g is equal to the min over theta of f, or the theta that minimizes f, the absolute value of f, given that f is equal to this, is defined as this. So what that will appear like when we actually do it is this absolute value f and its parameter theta will look at something like this. And over here, we take our minimum here and say that is definitely theta g, which gives us theta a, which is all we needed to solve the transmission angles. So job well done. Okay, now I'm going to switch over to MATLAB, and it'll be a cut in the video, so hopefully it isn't too abrasive. All right. So I'm going to go through setting up a quick example script for you. I'm just going to program it the way I usually program it. Hopefully you don't mind. Should be, sometimes a little verbose, but it'll be all right. So what I have here is I have set up a directory in the ONR work folder. So in the OneNote work folder, I have Kirchhoff Migration. I have an example data directory where I have the data of a B-scan that we measured very recently using the new sampling scope, and the metadata to go with that. So if we open this up real quick, go away, you'll see that this is a 2D matrix. This is the B-scan where the row is time and the column is scan number. And then this meta file that we're going to read in, this row here is X, or scan position, and then this row here is the time vector. So we're going to use this data, and we're going to create a script, 3 scripts that will implement the Kirchhoff migration. So I have pre-created empty files here. So we have the example bscan driver. So we're going to read in the bscan and process it. And then we have the Kirchhoff migration, which does the actual imaging. And then we have transmission angles, which we need for Kirchhoff migration. So transmission angles, I have images up on the video. Transmission angles solves this equation up here in the upper right, and then Kirchhoff migration implements this equation up here. Then both of them need this expected time. So let's get started. So we're going to read in the bscan first. Apologies, this is my second time doing it because last time I recorded it had a very poor quality. So but now I have a reference. So we're going to read in the bscans. So let's make a variable called directory and find what directory we read it in from. Take this, put a backslash at the end. And then our file name for our bscan is right here. Put that in .csv. Put a .csv there. Then our file name for the meta is .csv. So let's read them in. Reading bscan meta. Our variable will be called b, so the CSV read dir plus fnb. Then our meta matrix will be CSV read dir plus fnm. So let's break down the CSV matrix. So the x positions is the first row, if you remember. So we'll take that first row. This is positions of skins, but we have to do, for sanity's sake, I had to pad it with a bunch of zeros, so we have to include this code here. Find x1 less. This removes all the zeros at the end. And then, of course, the time is the second row there. So now we have the bscan in, so let's plot it. So this was taken with the Gen 6 ERLVDs. Actually, we don't need this hold on grid on. Let's just muscle memory go in there. Set the color map to gray to 12. That specifies the fineness of the gradient. And then we'll do image scale T29. We'll put a hold on. And for I'm just going to plot the entirety of the limits and the labels and the such. You could speed up through it if you want, or you could include them. I just like to make my plots nice from the get-go. 0 to max t. If for some reason the image scale looks bad if you don't put these limits on. So our x is scan position meters. Our y is time in nanoseconds, and this is the rawest we can get, raw bscan. So let's run this with this button up here and see what happens. What did I do wrong? Sorry. It should work. So, dir plus fnb. Okay. Well, sorry, I'll cut this out. Oh, there we go. There's a semicolon in the text. Okay. So we got our bscan in. You can see all the coupling region here. See the target hyperbolas. There's two, like we have usually been doing. For some reason, this setup had really bad coupling, so all the way to the edges, but of course when we have the data we're not concerned with that. That is the designer's issue. Okay, so let's do some pre-processing on it. Let's do background removal. So background removal is the easiest pre-processing method ever, but of course it never does a perfect job, as you'll see. So we just take B minus the average of B over the columns. So that's just taking this B scan and calculating for each row what the mean is for over all the columns. So the mean of this column will definitely be whatever this point is here. So 0.1069. So it'll definitely be that. So it'll remove coupling and most static objects. But let's do something a little more complicated. Because we are using an equivalent time receiver, we have some jitter residue. So we need to filter it. Let's do filtering in 2 dimensions. So this is our fs, which is our time sampling frequency. We can use that to make the frequency vector as such minus fs over 2, fs over 2, num L t. This is our frequency vector. Okay. Now let's do the spatial frequencies. So let's get our dx here and make our fx. So this is our spatial sampling frequency. And then our kx vector, which is the analogous vector of f, is length space minus fx over 2, fx over 2, num L x. Okay. So let's apply the filter in time. So we're going to use rectangular bandpass and high pass filters. So f high is equal to 5v9, so this is upper cutoff frequency. And then our lower cutoff frequency will be 600 megahertz. Lower cutoff frequency. Now, I'm going to say BKGR underscore F as in FFT'd once. Let's do F1 is equal to FFT shift FFT of BKGR brackets 1, comma 1. So this will do it the FFT and the FFT shift operation over only the first dimension. So now we're in FX domain. And then we can do the filtering operation here. So abs f greater than f high, comma, brackets is equal to 0. It's important to have that in there. Otherwise, we'll do linear indices and it'll be all wonky. And abs f less than f low is equal to 0. Okay, so this is now filtered in time with our bandpass filter characteristics that we specify right here. So now let's do spatial filter. This one usually gets rid of most of the jitter, in my opinion. So kx underscore high is equal to 30. We're going to do a low pass filter. So BKGR F2, it's been filtered twice. This is the FFT shift of the FFT of BKGR F1. Brackets 2, comma 2. So we're doing along the second dimension. Now we are in FK domain. So there's an analogous migration algorithm called FK migration. So if you were to do that, you would use something that's been FFT'd twice, such as this. Or if you took it in frequency domain. So BKGR F2 colon comma abs kx greater than kx high is equal to 0. So now this is filtered in time and space. Now let's convert back to the B scan. So this would be the TX domain. and we can call it BKGR underscore filtered. Now you can do this in one line. I'm going to do this in 2 lines of code. So IFFT, IFFT shift, BKGR F2, 1. So let's do the first domain first. Comma, brackets 1. So now this is the TK domain. And then BKGR filtered. Let's do it on itself again. IFFT, IFFT shift, BKGR F2, 2. But this time, let's put in a real here, just to clarify for any numeric errors. So this is now TX domain. And that's wrong. I want to put filtered here. Thanks for catching that. So now let's do a big subplot. Let's plot 3 subplots of BKGR scans. So we'll do figure 2, color map gray, B12. First subplot 131. We're going to have 3 in a row here. Let's do the image scale of X, T1E9, and just the BKGR. So this is basically raw, use quotes, raw BKGR. And I'm going to copy all of this stuff up here because it's really the same. But I will change BKGR. Okay, second subplot. 2. We're going to do image scale X T times 29 of BKGR filtered. So this would be the filtered one that has gone through all of our pre-processing steps. And again, I'll copy the same plot information, so this will be the filtered BKGR. Now finally, let's do something fun and spicy. Let's go with a FK plot, which will be very interesting. So KX for the x-axis, frequency in gigahertz for the y. Then let's do 20 log 10 of the absolute value BKGR F2. So that's this up here where it's in the FK domain and been filtered twice. But we want to normalize this for the sake of plotting. So let's do max of the absolute value of BKGR F2, index that with a colon. So it turns into vectors that we can take the max of. I'll put the whole on. I'm going to copy this, but you have to change a lot more. So xlim max kx, min kx, ylim, we have in frequency gigahertz, so let's do minus 5 to 5 with brackets. So this x label, we now have spatial frequency. I have a LaTeX interpreter on from the first part, so I'll do kx. And then y label is just frequency in gigahertz. And then this, we will call it the FK BKGR B scan. Let's see what that looks like. I'll run it. What? Went wrong. That is an uppercase. Oh my goodness. What did I do here? Oh, let me put in C-axis. So on the subplot here, C-axis, minus 30 0. I'll rerun it. Okay. So maximize this. So what we can see, this is, if we just do the subtraction, we have some residue up here. Of course, if we filter it, like that one paper we wrote, we get rid of that residue, and it still looks good. And we can see from the FK, most of our content is really below 3 gigahertz. This is 30 dB. And most content is less than 20. I just like to be conservative with that KX filter, because when you bring that KX filter all the way down to 20, it starts to kind of look like poop. So I like to keep it at a healthy 30. Okay, so now we have everything we need to start the Kirchhoff migration. So there's a long lineup. So let's perform the Kirchhoff migration. To do that, we will need a function, which I already have the file created for. But so we have to match the name Kirchhoff migration 2D here. And into that function, we will pass BKGR filtered, and we'll pass several more variables here: t, x, xq, zq. So what these variables are, obviously we know this one. So h is equal to 28e negative 2. This is height of antenna. ER is equal to 5.7. This is relative permittivity. T we know. X we know. XQ we do not know. This XQ and ZQ make up the vectors of query points. We're going to make a rectangular. It doesn't necessarily need to be rectangular, but we're going to make a rectangular image that starts from, it's basically XQ cross ZQ. So let's say we want to get XQ at every X that we have, and ZQ, let's do 0 with let's just see what that looks like. 5 millimeter increment down to 0.4. Let's see what it looks like. So now we have to make this function. So you probably don't already have a file created, but you just open up a new scan here, and then you'll have to create the function as such. So I'll just copy here, function I is equal to Kirchhoff migration 2D, and then we change the name of the input variables as so. So for the sake of completeness, I'm gonna specify what all the input variables are. So B, this is a pre-processed P-scan. H, antenna height. ER, relative permittivity. I'm not going to go for spelling. T is the time vector. XA is spatial vector from sampling. XQ is query points in X. ZQ, query points in Z. So our output will be I, which will be an image calculated at XQ cross ZQ rectangles, and this will be an absolute value. And rows should be depth, columns should be X. Q. So let's start here, and this is a somewhat complicated function. So let's start by creating some variables and getting sizes of things. So C is the speed of light, and T is number of elements in T, and XQ is number of elements of XQ, and ZQ is the number of elements in ZQ, and NXA, as you guessed it, number of elements in XA. Okay, so the goal of this is to calculate the kernel. I believe I have it displayed up above, the kernel of the Kirchhoff migration integral, and then integrate it. So let's initialize the kernel. The kernel is zeros, and this is nxa, nxq, and zq. So this dimension will obviously be the resultant image. This dimension is the one we integrate along. Okay. Close that. So we have to, in the proper Kirchhoff migration equation, it calls for a half derivative. So let's calculate the half derivative. And you'll see I kind of get rid of that later, but so the sampling frequency we have to recalculate in this function is here. And just like before, the frequency vector fs over 2 and t. So the frequency domain bscan, b sub f is the FFT shift of the FFT. B along dimension 1. So this will be fx domain. And let's do what is, we can, since we're doing this half derivative in frequency domain, we'll do an operator. So retmat, and we're going to calculate the square root of j omega when I times 2 pi f transpose. And then we're going to replicate that into nxa columns. So this is basically a bscan. The exact size as the bscan, except it is a differential operator. Then we'll say dB is the real part of the IFFT shift of d12 dot times b underscore f along dimension 1 along dimension 1. Okay. So I'm going to write this piece of code in a comment, bring up the screen a bit. So dB is equal to b. Now that's ridiculous, right? Well, actually, this looks better. dB is the half derivative. So if we just don't do the half derivative in general, I think the image looks better. But the proper Kirchhoff migration says let's do the half derivative. You know, sometime, I mean, most of the time I just uncomment this line. So we have dB is equal to b. So let's use this function that we copied, progress bar. I got this off the exchange. It's really useful. This will keep track of our progress. So Kirchhoff migration progress. And then let's start the proper loops. So for m is equal to 1 nxq. So we're going to iterate over xq query points. And then we'll select a query point as a lowercase xqm. Then we're going to, inside that loop, we're going to iterate over z for n is equal to 1 and zq. You know, of course, since we're using these loops, it's not that efficient for MATLAB. So there's definitely a better way, but I have not committed my time to finding a more efficient way. So this will take a couple minutes when you actually try to run it. So now we're at the point where we have to calculate transmission angles. So we need a vector of transmission angles for each xa point. So theta AV, let's initialize an array. 0 is nxa1. Theta GB, which is the ground angle, 0 is nxa1. So these are just empty vectors. And then let's iterate using p over nxa. So So now we need theta A. We need some function that returns air angle and ground angle. And let's call it the transmission angles function, because I have a file already set up for that. And that will put in ER, H, XQ, ZQ, and XA and XB. So this is the position of the antenna. This is the position of the target, XQ, ZQ, and then H we know, ER we know. And then we're going to take the result from this function that we haven't written yet, theta AVP is equal to theta A, theta GVP, theta G. Alright, now let's finally get to it and write that function. I do have the equation displayed up above me, so let's open this file. And we need to call it something like this. So function, let me name it as such, call it xt for x target. I'm not going to say the input outputs. Actually, I will name the theta A is angle in air, because it will get confusing. Theta G, angle in soil. Okay. So now what we're doing is we're calculating the transmission angles. The way we do this is with the search for a min procedure. So we're going to specify a search vector for theta GV, 0 to pi over 2 using 2 to the 11 search points. And then we apply Snell's law here for theta A. So arcsine of square root of epsilon times sine of theta GV. But this is going to ruin our lives because we have complex angles here. So inside these brackets we put a min of either that angle or 1. So now we can't have any complex angles in air because our dielectric is on the bottom. So this next line kind of combines a few lines. So we're going to search for the index of the minimum, which will give our solution. We're going to take the minimum of the absolute value of the function above me. So this will be abs xt minus xq. Actually, it makes more sense to call this xa. Xt is for x target, but xq is really our xt. Anyway, in order to not confuse you, let me continue. Zq dot times tan theta gv minus h dot times tan theta ab. And that should account for all the parentheses. And then our solution is theta A is equal to theta AB in min theta G is equal to theta GB in min. Right, let's save that and let's actually give it a test. So let's say A and G is equal to transmission in the console window of 5. Let's say we're 30 centimeters above. The target is at 0, 30 centimeters in the ground, and our antenna is -1 meters. Okay. So this is in radians, of course. But let's check if Snell's law applies. So Snell's law says that sine A should be equal to square root ER times sine G. So let's just calculate this value. Oh, we didn't define ER in the workspace, but I think we used 5, right? Okay, so that's equal to 0, which means that the results obey Snell's law. So that's enough for me to say, hey, that function works. Okay, back to the Kirchhoff migration code. So we have the angles. Now we can start to calculate some of the kernel values. So in the kernel, we need to calculate R, which is just the distance from the target to the antenna. And this is kind of used as a weighting. So you don't have, if you don't have some ghost images on top, when you have a hyperbola down below, the R kind of decreases the CQ times secant theta GV. The R will decrease the effect that that lower hyperbola has on the actual image. So, and then let's calculate the T expecteds. So the equation is up above me again. 2h secant theta AB divided by C plus CQ times secant theta GV divided by C times square root ER. Now here comes the fun part. Select the correct data from DB. This is the part where we trace out the hyperbola. So there's a couple ways to do this. You could do a for loop. For speed, I found it's actually easier to do just a matrix indexing, but it's a little more complicated. So we're going to calculate the indices that these T expecteds correspond to. So we'll take min of something along dimension 2, and that something will be absolute value of repmat T for nxa times 1 rows. And let's see where, then we're going to minus T expecteds. So this will return for each how to say, XA, for each XA, we're going to have the index of the corresponding time expected. So this is properly tracing out the hyperbola. To actually index it into the matrix, though, we need to make it into a linear format. So we'll do sub2ind, where it's subscript to index. And since we're indexing dB, we put in size dB. We have ins, and the column coordinates is just 1 to nxa prime, or transpose here. Okay, now we have all we need for the kernel, so we construct the kernel. Kernel colon mn is equal to cosine theta AB square root R times dB of lin ins. For keeping track of progress, let's update the progress bar down here and divide by nxq. And we're finally going to output I is equal to squeeze, because we had a 3D matrix, the absolute value of the integration here. So trapz is trapezoidal numerical integration. We're integrating with respect to XA. We're integrating kernel, which at this point, after we exit all the loops, it'll be filled up to a 3D matrix. And we're doing it along dimension 1. And we also transpose that result. Okay, so that will give us, hopefully, if I spelled everything right, that should give us a Kirchhoff migration image. So let's go back and see what happens if we press go. How long does it take? Okay, not too bad. In the meantime, while this is running, I'm going to write imaging, or image plotting rather. So I'll do it in a new section so I can use these run section buttons without having to rerun the image. So I like to plot the 20 log 10 of the image. So I make a variable 20 log 10 I, and I take the max for plotting reasons, max log I, index it to be linear. Our dynamic range that we want to view it with is 10, and in figure 3, we will plot the image scale of xq, zq, log I with the z-axis, mi minus dr, mi. How much time we got? Oh, we got tons of time. So let's do x label. Let's say this is x in meters. Y label, this is depth in meters. Let's title it. This is my first migration. Let's see how my first migration turns out. Okay, it finished. Press the run section button up here. Okay, yeah, looks pretty good. My first migration. All right. So let's compare it to some of the B scans over here, just to see where things come from. Maybe make this B scan a bit bigger. So quite clearly this target is from this target hyperbola. This is also a weaker target, but you can still quite clearly see the hyperbola. This is from incomplete removal of something. Why did it get removed incompletely? I'm not sure. Maybe if we look back at the raw B scan. It's like whatever it is up here. So I'm not sure why that got removed incompletely, but it did. So maybe if I did a different version, it would get fixed better. Or if you did a lower kx cutoff. But of course, you don't like to mess with the background removal too much. You kind of just accept this this stuff happening. So I did mention earlier that it does look better if you don't take the half derivative. So let me take a little snip of this real quick, just so we can compare the difference. So let's run it again. But in this case, let me uncomment this so we can see what it looks like when we don't take the half derivative. I mean, it's not proper, true Kirchhoff migration, but, you know, who's going to stop me? So, yeah, it would be worth looking into to making this faster. Of course, we can't do like any real-time imaging or anything. We can just decrease the resolution. I mean, this is already pretty, you can definitely see the pixelation. And when I do some reports and progress reports or papers, I completely jack up the resolution, and maybe migration can take like 10 minutes. So it is quite poor. Our scope now, though, gives us 2,700 time samples versus we used to have 500 time samples. So we could downsample that to make it quite a bit faster, because now we have to integrate 2,700 things versus 500 things many, many times. So I'll let this run and see what it pops out. This FK is kind of interesting. I never really looked at it this way, but I like looking at it this way now. Okay. So we've got our result here. Yeah, looks kind of the same. The only difference is, since we didn't take this derivative, the this here is a bit lower. But honestly, I prefer this one. I prefer this one, but it doesn't seem to really matter. Alright, so that's going to be the end. I'm going to leave my scripts in this folder. If you want to look at them, copy them. You should definitely copy this part at least if you just program along. So anyway, thank you for listening.